On the quiz, we had a question like this. If that's a vector equation that defines a movement, how fast is it moving? People who got it wrong seemed to have done something like this. They tried to memorize that a number in a particular position just tells you the speed. And that's not the case. In general, in this class, it's not going to work to try and memorize something without understanding how it makes sense. So for this question, every single question that's asking about speed, you can answer it just by going back to the definition of speed. Speed is just some distance traveled divided by how long it took. So for all of these questions I'm about to ask, every single time you can answer them just by saying, I went a certain distance, how long did it take? Or, for a certain amount of time, how far did I go? But if you can just answer those two, now you've got speed. So let's take a look. For these three vectors, they're all exactly the same except for how they're being scaled in the front here. So let's try and apply the idea. Let's decide a certain amount of time, 1 second, and let's ask, what distance did we travel in 1 second? Here's a Desmos visualization of that same vector equation. So I've got negative 5, 2, which is taking me here. And that's not being affected by time, so that vector is always there. And then if I'm going to add the time-scaled vector, remember vectors add end to end. So here I am at time 0, and when this is 0, that scaled this vector down to length 0, which is why we don't see it there. And then at time 1, there we are. I've added this over to up 1 vector. So between time 0 and time 1, I was at negative 5, 2, and I went over to up 1, to end at negative 3, 3. So I started here, ended there. So it looks like I moved along that diagonal, and it took me 1 second. So we just need to ask, what's the length of that diagonal? Because that's the distance that I moved in 1 second. And the distance of that diagonal is just the magnitude of that vector. So 2 squared is 4, plus 1 squared is 1, so that's root 5. So here I'm moving at root 5 feet per second. Okay, so what happens if you add a 2 in front? There's two ways of thinking about this. Well, it's really just one way of thinking about it. It's really just this thing up here. But remember, adding a 2 multiplied in front of a vector scales it to be twice as long. So if I wanted to multiply the 2 in, this would be the same as 4, 2. And so now, by that same thinking, if time is 0, this vector's length 0. If time is 1, that vector has a length that is 4 squared, which is 16, plus 2 squared, which is 4, so its length is root 20. So that means every single time t goes up by 1, I traverse that vector. I move along that vector whose length is root 20. So I should be going root 20 feet per second. A different way of thinking about it is every time t goes up by 1, I am moving along 2 of my original vectors. So if I'm moving 2 of my original vectors, I'm moving twice as far as if I just did 1 vector. So if I'm moving twice as far in the same amount of time, I must be moving twice as fast. So it should be the case also that I'm moving 2 root 5 feet per second, because I'm moving 2 of the root 5s in 1 second. Are these really the same? Absolutely. Let's show that they're actually the same. So 20 is the same thing as 4 times 5. If I apply the root to each of these parts separately, square root of 4 is 2, and square root of 5 is still square root 5. So you can see that I can turn the root 20 into 2 root 5, and they're really the same. Okay, so what about this one? Again, let's think about it in the same two ways. I could think about this 1/2 as making this vector scale down to be half as long. So in that case, the 2 divides the 2, and then this becomes 1/2. And so now every time t goes up by 1, I'm traversing the length of that vector. The length of that vector is 1 plus 1/4. If I rewrite the 1 as 4 over 4, because that's the same as 1, that gives me root 5/4. And now if I simplify that, that gives me root 5 divided by 2. Sorry, the square root covers everything there. So that's how many feet per second I'm going. You could also think about it this way. With every second, I'm going half as far. I'm going half the length of that original vector. So if I'm going half as far in the same amount of time, I'm going half as fast. So I can take my original speed and divide it by 2 because I'm going half as fast. Okay, but as a cautionary note, remember you always have to visualize what's happening. You have to ask, what does all this mean when you put it together? So if I ask this one, what's the speed I'm traveling here? Well, here I've got my original starting point vector, but now I have two different vectors that are being scaled with time. So one thing that you could do is you could try and combine those vectors together. So I could multiply the t in, so that would give me 3t, t. And then here I could multiply the t in, giving me t comma 3t. And remember, you can add vectors just by adding the x components and the y components separately. So if I add these two together, that's really the same thing as saying 3t plus t gives me 4t. And then here I've got 1t plus 3t gives me another 4t. Okay, so let's get our original vector back in there. So how has this helped us think? Let's take the t back out again. So here I'll have t 4, 4. And what that tells me is that every single second I'm traveling along the diagonal for the triangle over 4, up 4. So if every single second I traverse that distance is just square root of 16 plus 16, which is square root 32. It's maybe a little bit silly to do that. It's really just 16 feet per second. You could also have just graphed it out. So here, I'm going to visualize the sum of three vectors. I've got my negative 5, 2, not being time scaled. And then I've got this time scaled 3, 1, and the time scaled 1, 3. So here I am at time 0. At time 1, you see I'm adding the green vector, which is over 3, up 1, to the purple vector, which is over 1, up 3. But if I add all three of those vectors together, it takes me to this point at negative 1, 6. So at time 0, I was at negative 5, 2. At time 1, I'm at negative 1, 6. So you can see in 1 second, I moved along this invisible diagonal here because I started here and ended there. And that's over 4, up 4. And that over 4, up 4 is the same thing that we solved for on the piece of paper. That's the same thing that we got when we tried to combine these all together. But you wouldn't have had to combine them all together algebraically. You could have just imagined what's the vector when time equals 0, what's the vector when time equals 1, and then thought, if I'm moving diagonally, what's that total distance? Okay, well, what about these ones? You recognize these as being circular motion, but I'm not going to ask about the rotational speed. I'm not going to ask about how fast the angle is changing over time. I'm still going to ask about linear speed. And even if you're moving in a circle, if you're measuring your speed in feet per second, if you're measuring your speed as distance traveled over time, we're still calling it linear speed. Okay, so how fast am I moving if I'm moving along this vector? So I said that you could ask yourself, how far did I travel in a certain amount of time? And for these ones, I thought, where am I at time 0? Where am I at time 1? How far did I travel? So you can do the same thing here, but you have to think a little bit. Let's plug in time 0. So at time 0, I'll be at a vector that's cosine 0, sine 0. So if I'm sort of visualizing where that is, that's right here. So here I am at time 0. Where am I 1 second later? At time 1, I am at cosine, let's see, 2 pi times 1 is just 2 pi. Sine 2 pi. All right, so, 1 second later, it looks like I'm at that exact same spot. So unless you can actually visualize what motion is happening, it seems like my speed is 0, because at time 0 I'm here, and at time 1 I'm still there. What you have to think about is, over the course of that 1 second, I have gone through a full circle here. So again, if I want to know how fast I'm going, I should ask, what distance did I travel in that 1 second? If I want a full circle, let's figure out what's that total circumference length. So circumference is 2 pi times the radius. In this case, the radius is 1. So the total distance I went was just 2 pi. So in this case, my speed is 2 pi feet per second. What about this one? For this one, at time 0, my angle is 0. Let's make a little sketch here. So here I am at time 0. At time 1, my angle is pi, which is pointed over here. So it seems like in 1 second, I went halfway around the circle. The total circumference of the circle is 2 pi times 5. So the total circumference is 10 pi. But I only went half the circumference. I only went 5 pi in the 1 second. So it must be that I'm traveling 5 pi, I don't know why I did a slash there, 5 pi feet per second. So again, I think all of these questions are pretty simple if you always just ask, how far did I go? How long did it take? And the only tricky part is you can't just look at these as numbers. You actually have to look at this and imagine what's the motion that it defines. So let's end with one more. What about this one? Here I have a time-scaled vector, and here I have a circular vector. So you might try and do a lot of stuff here, but if you imagine the path that's being taken, this vector is just stretching continuously to the right with time. So at time 0, it'll be length 0 here, and then at time 1, it'll be length 5 pointed to the right. So here's time equals 1. Okay, what's this one doing? This vector is rotating 1 full circle every second. So at time 0, its length is 1. So at time 0, it's here. And over the course of 1 second, it makes 1 full rotation. So what's it look like if I add those together? Let's visualize what happens at time 0 and time 1/2 and time 1. So at time 0, if I add those two vectors together, I've got length 0 plus a right-facing vector that's length 1. So here I am at time 0. Oh, there we go. Where this is length 1 there. Okay, at time 1/2, this has stretched to be 2.5 long to the right. So let's make this be like 1, 2.5, about here. And this vector has rotated a half of a circle. So it's now pointed 1 to the left. So if I add those together, 2.5 this way and 1 to the left, that puts me about here. Time equals 1.5. You know what? I've chosen these poorly because at time equals 0 and 1, we still don't have any y coordinates here. So actually, instead, let's go to Desmos for a minute. Okay, here we go. So let's visualize what happens when you add the stretching vector and the rotating vector between time 0 and time 1. So here's time 0, and as you can see, as I'm going to time 1, we've got the horizontal, and I'm going back now, we've got the horizontally stretching vector, and we've got the rotating vector. So if we ask what's our speed, what we need to know is that total path that I travel, how far is that path? Here's what the path looks like. So let's watch it again. Starting from right here at x equals 1, it makes this little curly Q loop, and then across there, and then kind of ends there. Okay, well, there isn't any really obvious way, just by looking at it, to figure out what the length of that path is. So I think in this case, we should decide that there isn't a particularly good way to answer this question. Maybe if it's math, so maybe if you thought about it, you could come up with some clever way of figuring out how long that path is. Like maybe it turns out to be equivalent to parts of circles or part of an ellipse, if you know how to think about the perimeter of an ellipse. But the idea is, if you understand a concept, I want you to be able to look at a question and say, oh, we can't answer this question based on what we know. So up here, we could give the speed because this was just linear motion. And here we could give the speed because it's circular motion, and we can calculate what's the distance around the circumference. Here, when you're adding them together, now the path that you travel doesn't really have a length that's easy to calculate. And so because we can't know the distance we traveled in a certain amount of time, we just don't know what our speed is. So that's a complete set of ideas for thinking about speed, and hopefully it feels a little bit easier now than it did at the start of the video, but it really all just comes back to the definition of speed. I hope this helped.